Hello, and welcome to Astronomy with Mr. Guerin. Today we're going to talk about aliens. We'll consider where they might live and what their biology might be like. We'll talk about a few likely places to find life, in and outside our solar system, and how likely it is that alien life exists. And we'll finish with a discussion on whether it's a good idea to go looking for aliens. Extraterrestrial life means life that originated outside of Earth. It doesn't include astronauts or accidental contamination of other bodies, such as the tardigrades scattered on the moon's surface when the Israeli lander Bereshit crashed in 2019. The idea has long fascinated humanity. The ancient Indian religion of Jainism and some interpretations of Islam hold that the universe is infinite and many other worlds are home to life and intelligence. In the 17th century, Galileo Galilei showed that the Earth is not the center of the universe, and many scientists began to take seriously the idea of alien life. In the 19th century, science fiction literature started to heavily feature alien life, and in the 20th century, many people reported encounters with aliens and even abductions by them. Curiously, although there were many photos taken of aliens and their spacecraft, they tend to be blurry and out of focus. And since we all started carrying high-quality cameras in our pockets, these beings have become much more shy. And in 1984, the SETI Institute, the Search for Extraterrestrial Intelligence, a serious scientific endeavor, was founded. Outside our solar system, we generally assume aliens must live on planets. An extrasolar planet, or exoplanet, is a planet outside our solar system. The first exoplanet was confirmed in 1992. The first observation of an exoplanet was actually a photograph in 1917, but this wasn't recognized until 100 years later. Today, we know of thousands of exoplanets, including some in other galaxies. At first, we only found very large exoplanets, bigger than Jupiter, since large planets are easier to find. Over time, our techniques improved, and now can find planets as small as Earth, or sometimes even Mercury. This artist's impression, with the stars and planets magnified for visibility, shows just how densely populated our galaxy might be. Most exoplanets are discovered indirectly, rather than by an actual photograph of the planet. We'll consider four of the main methods of discovery: direct imaging, transit method, astrometry, and radial velocity measurements. Direct imaging is actual photographs of a planet. Only 29 exoplanets have been found this way so far. This is extremely difficult, as an exoplanet's light is very faint and tends to be swamped by the light from the star. It is only useful for nearby star systems and for large planets close to their parent star, so that the planet reflects a lot of light. We block the star's light with a coronagraph, a small disk of plastic or metal, and take multiple images which are combined with a computer to intensify the planet's faint reflected light. Here we can see the motion of 4 planets, each many times more massive than Jupiter, over 7 years. This system is 128 light-years away. Thousands of exoplanets, about 3/4 of the total, have been discovered using the transit method, including 7 planets in the celebrated TRAPPIST-1 system, 40 light-years from Earth. If a planet's orbit is aligned with the Earth, the planet may pass in front of its star from our perspective. As it does so, it blocks out a tiny amount of the star's light. We can observe the star over time and measure the change in light. We call this change over time the star's light curve. The transit method can tell us the size of the planet and its orbital period. If we know the star's mass, we can also calculate the planet's orbital radius, how far it is from its star. Astrometry, or star measurement, is the measurement of a star's position in the sky. We say that planets orbit stars, but this isn't precisely true. Planets and stars orbit their combined center of mass, their barycenter. This makes the star wobble slightly. The motion of the star is greater for high-mass planets orbiting low-mass stars. Astrometry has a few advantages compared with the transit method. It can be used for stars whose ecliptic isn't aligned with Earth, and can detect planets far from the star, where they are too dim to be found by other methods. It can also tell us the mass of the planet. However, the wobble of stars is very tiny. Detecting planets by astrometry is very hard, and a total of 1 exoplanet has been discovered and confirmed with this method, and even that has been disputed. The radial velocity method also uses the motion of a star caused by an orbiting planet, but in a different way. As the star moves towards us, its light becomes slightly blue-shifted, and as it moves away from us, its light becomes slightly redshifted. This is called the Doppler effect, and I'll discuss it in more detail in a future video. By observing the tiny changes in the wavelength of light received from a star, we can determine its radial velocity towards or away from Earth. Observations of this change over time can tell us the orbital period of the star and planet around their barycenter. Here, you can see that the radial velocity peaks 0.5 and 2.5 years after our measurements began. The orbital period of the planet is the difference, 2 Earth years. Like astrometry, the radial velocity method can tell us the mass of the planet, and is most effective for high-mass planets orbiting close to their parent star. But unlike astrometry, the radial velocity method works, and so far we have discovered over 800 planets using this method. So now we know how to look for planets. But what should we look for as evidence of life? Most astrobiologists believe that life must be carbon-based. Carbon can form 4 bonds, making it very versatile, able to form complex chemical structures in long chains. This is what allows it to create proteins, such as DNA. Other elements can form long chains, such as silicon, which is in the same group as carbon on the periodic table. However, silicon is rarer than carbon and bonds with fewer elements, making it harder to form complex molecules. For now, it seems that alternate biochemistries, such as silicon-based life, remain the stuff of science fiction. Life must also have a solvent, a chemical which can dissolve other chemicals and transport them within cells and around our bodies. The most suitable solvent is liquid water. It's the most common compound in the universe, and its chemical properties are perfectly suited to life. Indeed, water has been called the solvent for life and the matrix for life, so we generally assume that all life requires water. Other solvents, such as methane or ethane, have been proposed as alternatives to water, and we'll discuss those shortly. In the Old English folk tale, Goldilocks tried Papa Bear's porridge, but it was too hot for her. Then she tried Mama Bear's porridge, but it was too cold. Finally, she tried Baby Bear's porridge, and it was just right. If liquid water is going to exist on a planet, the temperature must be just right. Too close to the star, and it will be too hot, and the water will boil. Too far, and it will be too cold, and the water will freeze. The region around a star where the temperature is right for liquid water is called the Goldilocks zone, or the habitable zone. In our solar system, Earth and Mars are in the Goldilocks zone. Some of Jupiter's and Saturn's moons are also warm enough for liquid water, as tidal heating from their planet melts the ice. In the 19th century, astronomers looked at Venus with improved telescopes and saw that it was a cloudy planet. Well, they thought, where on Earth do we see lots of clouds? The answer was, of course, rainforests, places teeming with life and biodiversity. For years after, scientists and science fiction writers alike assumed Venus was a jungle planet. The Guzman Prize, announced in 1900, was 100,000 French francs to be given to the first person to communicate with extraterrestrial life. However, communication with Martians was specifically excluded because it was considered too easy. We've now visited both Venus and Mars and found no evidence of life. Phosphine gas was discovered in Venus's upper atmosphere in 2020, possibly evidence of bacteria, but further analysis indicated this was a false detection. These days, we're more interested in the moons of Jupiter and Saturn. If you're doing the astronomy GCSE, you should know about Titan, Europa, and Enceladus. Titan is Saturn's largest moon, and the second largest moon in the solar system, larger even than the smallest planet, Mercury. Titan has a thick atmosphere, mostly nitrogen, with lots of methane and ethane, and oceans of liquid ethane and methane on the surface. These oceans contain complex hydrocarbons. Recreating these conditions in labs on Earth led to the formation of nucleotide bases, the building blocks of DNA. The surface has ice but no liquid water, but below the surface may be oceans of liquid water or ammonia, so simple life could exist both on and beneath the surface. But some scientists point out that Titan is very cold, about 94 Kelvin on the surface. This would make it very difficult for life to form there. Europa is the smallest of Jupiter's Galilean moons, but still the 6th largest moon in the solar system. The atmosphere is very thin and mostly oxygen. Its surface is extremely smooth water ice, and it's unlikely that life could form there. But beneath the surface, tidal heating has melted the ice, creating a salty liquid water ocean above Europa's rocky core. The Moon may also have underwater volcanoes, similar to hydrothermal vents. Such places at the bottom of Earth's oceans harbour life quite different from life on our surface or in shallow water. On Europa's surface are clay-like minerals and hydrogen peroxide, chemicals which can be produced by life processes on Earth. However, some scientists think Europa's oceans are just too cold or too salty for life to develop. In Arthur C. Clarke's book 2010 Odyssey 2, as well as the film based on it, astronauts find aquatic life beneath Europa's surface, which eventually develops into an intelligent civilization. Enceladus is Saturn's sixth largest moon. It is covered in freshwater ice, and at the South Pole, cryovolcanoes shoot jets of water vapor and other material, which created one of Saturn's rings. Enceladus is geologically active. Beneath the surface, volcanoes have melted the ice, creating a saltwater ocean which covers the entire moon. Beneath the ocean is a rocky core, and above it a 30-kilometer thick ice shelf. In 2005, the space probe Cassini passed through the cryovolcanic plumes, which erupt continuously. Its chemical analysis found many organic molecules, including methane, ammonia, benzene, formaldehyde, and larger complex organic molecules. On Earth, these chemicals are strong indicators for the presence of life. Although we haven't found life yet, Enceladus is a very promising candidate, and space agencies are considering a submarine probe in the future. Where are all the aliens? This question was asked by Enrico Fermi, an Italian-American physicist in 1950. Although not part of the GCSE course, his question, known as the Fermi paradox, is crucial in understanding our search for life. There are billions of stars in the Milky Way. Most have planets, and we have already found hundreds that look like they could support life. And many of these planets are much older than Earth, so they've had plenty of time to develop intelligent life. Humans could start sending people to other stars this century. Once we've colonized a star system, those colonists can send more colonists to more stars, and so on. Even with current physics, we could colonize the whole galaxy in a few million years. So in the 13,000 million years the Milky Way has existed, aliens could have easily reached every corner of the galaxy. So, why haven't we seen them? In 1950, Fermi was talking only about the Milky Way, but since then we've considered life in other galaxies. Soviet astronomer Nikolai Kardashev proposed a three-point system for classifying the technological development of a species in 1964 called the Kardashev scale. A Type 1 civilization can use all the energy available on their home planet, capturing all their star's radiation that reaches their planet. This is equivalent to covering the Earth with solar panels, and provides about 10 to the power 16 watts. A Type 2 civilization can use all the energy produced by their star. They build a Dyson swarm, millions of solar collectors surrounding their star. An entire star provides about 10 to the 26 watts. A Type 3 civilization has colonized their galaxy, building Dyson swarms around every star. The combined power of the galaxy provides about 10 to the 36 watts. Note that this is a logarithmic scale, meaning an increase of 1 on the scale multiplies the power from the previous number. Humans currently use about 10 to the 12 watts, putting us at about 0.7 on this scale. Most galaxies are at least twice as old as the Earth, so there are billions of habitable planets much older than ours, with plenty of time in the past to develop life, intelligence, and technology. As a civilization moves from Type 2 to Type 3, it envelops its stars, making them gradually disappear from view. As the civilization expands, a dark bubble grows, originating at the home system of the civilization. So when we look at other galaxies, we see that many of them have a chunk missing, indicating that it's home to a Type 2-point-something civilization. Except we don't see that. Out of millions of galaxies observed by humans and billions observed by computers, not a single one has a hole like this. Why not? You don't need to know the Fermi paradox or the Kardashev scale for the astronomy GCSE, but you do need to know the Drake equation. Frank Drake is an American astrophysicist, not to be confused with the explorer Sir Francis Drake. In 1961, he devised the Drake equation to estimate how many extraterrestrial civilizations we can communicate with. He considered only the Milky Way, as aliens in other galaxies are too far away for realistic communication. The Drake equation consists of 7 factors which we multiply together to get n, the number of civilizations we can talk to. There are a few versions of the equation. This is the one used by the GCSE, and we'll consider each factor in turn. As I talk through the factors, you might want to write down your estimates for each of them. At the end, you can multiply them to get your own value for n. R star is the rate of star formation in the Milky Way, the number of new stars per year. This figure is pretty well understood and is somewhere between 1.5 and 3 stars per year. Choose your own number within this range. F stands for fraction, and Fp is the fraction of stars that have planets. In 1961, no exoplanets were known, but we now understand that virtually every star has planets. Fp is about 1. Ne is the number of Earth-like planets that could support life, for every star that has planets. From our previous assumptions, this means lots of carbon, liquid water, and a location in the Goldilocks zone. We're only considering planets here, as no extrasolar moons have yet been found. The Kepler Space Telescope operated from 2009 to 2018, and gave us a much better understanding of this number. There are 40 billion suitable planets around 100 billion stars, so Ne is about 0.4. Fl asks, of those planets that can support life, what fraction does develop life? So far, our factors have been pretty clear with good estimates. They start to go downhill from here, as we have only one example to look at, and by definition, Earth developed life, or we wouldn't be here to ask the question. Optimists point out that life developed on Earth pretty much as soon as conditions allowed it to, as soon as planet-disrupting asteroids died down 3.7 billion years ago, or even earlier. This suggests life develops wherever it's possible, and Fl is close to 1. On the other hand, all current life has evolved from a single common ancestor. Life developed just once, rather than many times at different locations on Earth. Some biologists dispute this, but if it's true, it means that life is a rare event, and Fl is closer to 0. We can update this as we look for life elsewhere. Just one microbe found under Europa's ice would put our estimate closer to 1. But in the meantime, you can put your own number in here. Next, Fi is the fraction of planets with life that develop intelligent life. It's notoriously hard to define intelligence, and even harder to assess how likely it is. But Earth life was generally simple, single-celled organisms for most of history, for 3 billion years until the Cambrian explosion 500 million years ago. And even then, intelligence took a long time to emerge. Our first tool-using ancestors developed only 3 million years ago. If we find primitive life elsewhere in our solar system, this would indicate that life is more common, Fl is higher, but tends not to develop intelligence, so Fi is lower. Until then, again, you can choose whatever number you prefer. Fc is the fraction of intelligent life that produces civilizations. Historians and philosophers have argued for centuries over what a civilization is, but for our purposes it's very clear. A species that produces radio transmissions. Radio waves are the only viable way we can communicate with aliens. We've sent a few space probes out of the solar system, but it's almost impossible that an extraterrestrial species would find them. We've sent a few deliberate radio messages into space, directed toward possible locations for life, but most of our radio communication is just leaked signals from media broadcasts. Our best receiving technology could only detect our signals from about a light year away, only a quarter the distance to our nearest star. And in 300 million years of tool use, we've only had radio technology for 120 years. Fc appears to be very small. Drake proposed a value of 0.2, but it's up to you to decide if that seems appropriate. Lastly, L is the length of time civilizations produce these detectable signals, measured in years to balance the per-year unit of star formation, R star. As mentioned, we've only been producing radio signals for a little over 100 years. That's nothing compared to the lifetime of the galaxy. And as technology improves and gets more efficient, we actually release less radio waves into space. Perhaps intelligent civilizations don't last long. Our species currently has the technology to wipe ourselves out. Or perhaps they last a long time, but don't produce much radio transmission. Estimates of L vary, but are generally around 300 years. The truth of this is unclear, however, since only one known species has developed radio technology, and we don't know when we'll stop using it. Again, you can make up your own mind. The Drake equation is very controversial. Some astronomers like it, while others think it's a load of rubbish. It's a great starting point for understanding the possibilities for alien life, but it has a lot of unknown factors. Using different values for each factor, estimates vary from thousands of civilizations in the Milky Way to 0 in the whole universe. Some factors are very well known, some are quite unknown, and some we may never be able to know well. Here, I've color-coded the equation to show this. Note that this is my opinion, and you may well disagree. The rate of star formation and the fraction of stars with planets are very well defined. The number of Earth-like planets, the proportion of intelligent life that develops broadcasting civilizations, and the lifetime of such civilizations are poorly understood, but we can learn more about them. And the fraction of Earth-like planets with life and the fraction of life-bearing planets that develop intelligence are virtually unknown, for now at least. Scientists wondering about the lack of extraterrestrial life have developed the concept of a great filter. This bit isn't part of the GCSE. A great filter is a specific step somewhere along the path from the formation of planets to the development of an interstellar civilization that's so unlikely as to be essentially impossible. Interstellar life might be so rare that we'll be the first species to achieve it. If we continue to find no evidence of life outside Earth, then we have probably passed the great filter already. Perhaps life is extremely rare, or life is common but doesn't progress beyond single-celled organisms. Maybe the galaxy is filled with complex but unintelligent life. However, if we find that life is abundant, this increases the possibility that the great filter lies in our future. There are thousands of intelligent species, but they don't achieve interstellar travel. Maybe it turns out to be much harder than we thought, even impossible. Or perhaps species eliminate themselves through nuclear weapons, environmental destruction, or even some as yet unimagined technology that backfires and destroys them. Arthur C. Clarke said, "Two possibilities exist. Either we are alone in the universe, or we are not. Both are equally terrifying." Astronomers have been actively searching for signs of intelligent life for some time, since about 1960. This search is called the Search for Extraterrestrial Intelligence, or SETI, and in 1984 the SETI Institute was founded to expand the search. This search is mostly done using radio telescopes to detect deliberate transmissions, but also other telescopes, including optical telescopes, to find signs of life, such as biological chemicals around distant stars and planets. We have also sent deliberate communications out into space. In 1974, Frank Drake and Carl Sagan sent the Arecibo message, a digital radio signal that shows our solar system and some human biology. And the spacecraft Pioneer 10 and 11 have an engraved plaque, also designed by Drake and Sagan, that shows two humans and describes our position in the Milky Way. Both of these messages include mathematical information that should help aliens to understand them. The Arecibo message will reach its target in about 25,000 years, and Pioneer 10 will encounter another star system in 90,000 years. Don't hold your breath waiting for a reply. So far, we have found no evidence of aliens, but there have been a few tantalizing discoveries. We generally expect that an alien species deliberately trying to communicate with other life will use radio waves at a frequency of 1420 MHz. This frequency is emitted by hydrogen, so all astronomers are likely to know it and look for it, regardless of their planet of origin. In 1977, the Big Ear radio telescope detected a signal at this frequency in the direction of Sagittarius. The telescope recorded radio intensity as numbers on a printout, typically 0 to 4, but this signal was so strong it went up to 30, so high it was recorded with letters. The signal was detected for over a minute, until the telescope was no longer pointed in that direction. The astronomer who reviewed the data a few days later was so amazed he wrote "Wow" on the printout. We now know this as the WOW signal, and there is still no widely accepted cause. Somebody claimed in 2017 it was from a comet, but this was proven wrong. Unfortunately, the signal has never been detected again, despite many searches of that part of the sky. In 2015, American astronomer Tabitha S. Boyajian announced irregular fluctuations in a star 1,500 light-years away. This means it changes brightness in a way we can't explain, and this star is now called Tabby's star. Most stars fluctuate a small amount in a predictable way. Tabby's star's brightness dips by a huge amount, suggesting something much larger than a planet is blocking its light. But these changes don't occur in a regular pattern. So far, there have been several explanations, but none are completely satisfactory. And some have suggested that the star is surrounded by a Dyson swarm of solar satellites. Sadly, more recent analysis suggests this is probably not the case. So, we've talked about where to look for life, what to look for, and how to look. We'll wrap this up with perhaps the most important question. Should we look? Scientists, philosophers, and science fiction writers have often explored alien contact. Many think it would be positive for us as a species, but many others think it would be disastrous. Should we try to communicate with extraterrestrials, or try to hide our existence from them? Stephen Hawking said, meeting an advanced civilization could be like Native Americans encountering Columbus. That didn't turn out so well. On the other hand, the more optimistic Carl Sagan said, it is pointless to worry about the possible malevolent intentions of an advanced civilization with whom we might make contact. It is more likely that the mere fact that they have survived so long means that they have learned to live with themselves and others. Neil deGrasse Tyson says, all this fear-mongering of aliens in movies, this is not from any actual knowledge of aliens. It's from actual knowledge of humans. And Pope Francis was very inclusive, saying, any entity, no matter how many tentacles it has a soul. Let's communicate with the aliens. Any alien species we can talk to is most likely much more scientifically advanced than us, and they might cooperate and share their expertise with us. Scientifically, they could help us cure diseases, develop better interstellar travel, or teach us more effective ways to feed ourselves and protect our planet, among many more possibilities. They might also benefit our society. Perhaps we could share our different cultures, art, or even music. They may be more advanced politically and help us in our quest for a better, more peaceful world. And even if they don't choose to talk to us, the knowledge that such species exist could encourage cooperation and optimism in our own society. Let's hide from the aliens. Lots of people, especially science fiction writers, have discussed the possible harms that could come from finding aliens. They may decide to invade our planet and plunder our resources. They might be frightened that we could become a threat to them in the future and decide to wipe us out. Any species that can travel the stars to visit us could do this in any number of ways. They might deliberately, or even accidentally, introduce harmful diseases such as bacteria to Earth. We would have no natural immunity to alien diseases. Contact with extraterrestrials might also harm our society. People could become obsessed with the aliens' culture and neglect our own, especially if they are perceived as superior. Earth has no single global leader, so there might be power struggles over who gets to represent Earth to the rest of the galaxy. And the simple knowledge that life exists outside Earth would pose a significant challenge for many religious groups. You should be able to consider the pros and cons of meeting extraterrestrials and come up with your own opinion. Indeed, this is a requirement for the GCSE. But I'd like to give my thoughts on this one, and you may well disagree. I think extraterrestrials are very unlikely to try to destroy us. This idea comes from the knowledge that competition for space and resources on Earth is fierce. But the Milky Way is enormous, and there are plenty of planets richer in resources than Earth, even in our own solar system. There's just no point invading a world just to steal our stuff. Neither would they bother enslaving us. Any species capable of crossing interstellar distances and waging war on humanity will have robots far better than humans at whatever task they want to achieve. If the aliens wanted to appropriate our culture, art, music, literature, movies, and so on, they'll want us to live, and indeed thrive, to keep producing more. And remember, there's always a bigger bully. If there are two civilizations, there are almost certainly others. If one species starts throwing their weight around, perhaps a quiet but even more advanced group will come out and destroy the aggressor. If we've thought of this, then surely any other spacefaring civilization will have thought of it too. The possible destruction of your entire species is a great disincentive to murdering others. I leave you today with this final thought. If we truly are alone in the universe, I like to think that we're not the only life, rather, we're the first life. In that case, we have a great responsibility to lead the way for those who come after us. Thank you for watching. Goodbye, and have an excellent day.